Lesson 3.2 is titled Polynomial Functions of Higher Degree. In this lesson, we'll take a look at some of the ideas of quadratics and apply them to higher ordered polynomials. The first thing we're going to do is look at what's called end behavior. What happens on the left side of the graph and the right side of the graph as x goes towards negative infinity and positive infinity. To determine our result, we're going to apply what's called the leading coefficient test. The leading coefficient test is used to describe end behavior. And this will help us sketch our graphs. The first thing we look at is the type of function you have. So as you're looking at a polynomial, if the polynomial has an end value that's odd, which means the degree of the function, something like this. If you have y equals a times x to the third, the degree of the function is an odd number. Notice the arrows go in the opposite directions on both graphs. So on the left side and the right side, they're going in different directions. To figure out which direction matches with which, you look at your lead coefficient. If the lead coefficient is positive, then on the left side of the graph, it falls. And on the right side of the graph rises. So we can use that infinity notation, but we'll describe it as left and right rises and falls, just so that we get a rough sketch of our graph. This is when a is positive, so we'll say greater than 0. For the picture on the right, a would be negative. It goes in the other direction. So if your lead coefficient is negative, now on the left side, it rises. And on the right side over here, the graph falls. We'll literally be asked to describe end behavior and say, well, the left side it does this, the right side it does this. The other option would be when you have a polynomial that's classified as an even function. So something like a quadratic or a quartic. So like maybe y equals a times x to the fourth. So if your degree is an even number, now both arrows go in the same direction. They'll either both point up or both point down. And you'll get that answer again from your lead coefficient. In that first picture, your lead coefficient would be greater than 0. So on the left side, the graph rises. Well, there should be an R right there. And on the right side, it also rises. That's when A is positive. If a is negative, and we've worked with that with quadratics, but it applies to any even polynomial, on the left side and the right side, the graph will fall. Oops, for right, there we go, and we'll say falls. So what you're looking for is first, what is the degree of the polynomial? Classify it as odd or even. And then what is your a value? Is it greater than 0 or is it less than 0? And your answers will only be one of those 4 choices up above. All you need to do is match the degree and the a value or the a type and determine the left side, right side end behavior. Let's try a couple of examples. Describe the left-hand and right-hand behavior of the graph of each function. Our first function is f of x equals negative x cubed plus 4x. Looking at that lead term, it's written in standard form, our lead term is negative x to the third power. To think about our degree, if the exponent is 3, that's an odd number. So this is classified as an odd function. The negative out in front means a is less than 0. That's all we need to figure out, you guys. Once we know this, then we look up above, we describe the left side behavior and the right side behavior. That's literally all we do. This matches closely to that second function in our list of end behavior options. On the left side, this graph rises, so it goes towards positive infinity. And it may have a turning point or two, but then over on the right side, the graph will fall, which means it goes towards negative infinity on the y-axis. And that's it. This is our answer. On the left side, it rises, and on the right side, it falls. Let's try the next example. For our next function, g of x equals 2x to the fourth minus 5x squared plus 4. Taking a look at our lead term, The degree is the exponent of that lead term, which is 4, and that's an even number. So this is an even polynomial. Our a value is positive 2. That just means a is greater than 0. Now we just need to match up the option. This looks like it's closest resembling option 3 in our choices up above. Therefore, on the left-hand side of the graph and on the right side of the graph, it'll rise both times. So it goes up towards positive infinity on both sides of the function. Last one, h of x equals 1/3 x to the 5th minus x. 1/3 x to the 5th minus x. Again, we start by identifying our degree. The exponent here is 5. That's a quintic function, but it's also going to be an odd function. The a value, that lead coefficient, is 1/3, and that is greater than 0. Remember, anything that's an odd function, the arrows will actually go in opposite directions. This set of inputs, or this set of information, is most likely resembling that very first option for us. That means on the left side, the graph will fall towards negative infinity, and on the right, it will rise. And that's using left and right-hand behavior to describe end behavior of a function. Up next, we have real zeros of polynomial functions. There are lots of terms that describe what a zero is for a function. You could just say 0. You could also say solution. And if you change the sign in the inside, you could say that you have a factor of a polynomial. If you write it as an ordered pair, last but not least, you could have an x-intercept. All of those terms are synonymous to finding the zero or the root of the function. To determine what your zeros are, this is nothing new. We've done this before. Set the equation equal to 0. And then you want to factor completely. So make sure if you have any common factors, you take those out. And then look for maybe solving by, maybe look at factoring with quadratics, whether you do the a times c split the b rule or something like that. But your goal is to factor completely. Once you get that, you want to apply what's called the zero product property. And what that means is you're just setting each kind of term or part equal to 0 separately. Those solutions will tell you where your x-intercepts are on the graph. Find the zeros of f of x equals negative 2x to the 4th plus 2x squared. So the first thing we want to do is take this function and set it equal to 0. And then the next step is to try to factor completely. Taking a look at that first term and the second term, they have a pretty big common factor. They both have a 2 in common. They both have x to the 4th, or x squared in common, And I'm also going to factor that negative out. And that way, with what's left over, my lead term on the inside of the parenthesis will be positive. So if I factor out negative 2x squared, we would have x squared minus 1 left over. Well, this is a difference of 2 perfect squares, so that's going to factor even further. X squared minus 1 factors apart into x plus 1 and x minus 1. We still have that negative 2 x to the x squared on the outside, and then equals 0. We took negative 2x to the 4th plus 2x squared and factored completely. The last part of this solving process is to apply the zero product property. So I'm going to set negative 2x squared equal to 0. If you divide both sides by negative 2, that really doesn't do much. You get x squared equals 0. And if you square root each side, you would get x equals 0. But technically it's x squared, so it counts for 2 answers, even though 0 is only 1. So what I'm going to write is that has a multiplicity, or a multiple of 2. And that's going to mean something unique on our graph. All right, let's go on to the next one. The next two are pretty easy. If we set x plus 1 equal to 0, it'll cross the x-axis at negative 1. There's an answer. And then if we set x minus 1 equal to 0 and add 1 to each side, we'd get x equals positive 1. There's our other answer. So we have 3 different x-intercepts, but one of them has a multiplicity of 2. All right, let's use that information to sketch the graphs of polynomial functions. To sketch the graph of polynomial functions, the first thing we're going to want to do is determine our end behavior by applying that lead coefficient test. What's happening on the left side, what's happening on the right side. From there, we'll find our zeros, making sure that if we have multiplicities, we state them because that means something on our graph. The third step's super easy. Calculate the y-intercept. Just plug in x equals 0 and simplify. And then using that information, believe it or not, that's enough to draw a really quick sketch of our graph. All right, let's try the example down below. Sketch the function or sketch the graph of f of x equals 3x to the fourth minus 4x cubed. The first thing we're asked to do is describe that end behavior. That means we need to know what our degree and the a value is for that lead term. Our lead term is 3x to the fourth. Since the degree is 4, it's an even polynomial. And since a is positive 3, that means a is greater than 0. Think about what the left side and right side behavior will be. If you look at that chart on the first page, since it's an even function, the arrows should go in the same direction. And a is greater than 0, it's positive, so on the left side, the graph will rise. And it does the same thing on the right. And that's it for end behavior. For our zeros, we're going to apply the rules from up above. We're going to set our equation equal to 0, 3x to the fourth minus 4x cubed. Now let's see what we can factor out. We can't take anything out of the 3 and the 4, but we can take out an x to the third. This is going to be a pretty interesting looking shape for us. If we factor out x to the third, we have 3x minus 4 left over. And that's it for factoring. That's all you can do. But when you apply that zero product property, if we set x cubed equal to 0, technically that means 3 of our zeros are going to be the same number. This only works when x equals 0. But because of this 3 right here, we have to say a multiplicity of 3. We'll talk about what our graph looks like on that in just a second. If we set 3x minus 4 equal to 0, there's no exponent there, we'll just add 4 and then divide by 3. So x will equal 4/3 or 1 1/3, so slightly past 1. Let's go ahead and plot these points, 0 and 1 1/3. I'm going to make my graph a little bit bigger just so it's easier to see where those points are located. So I zoomed in just a little bit and put a point at 0 and a point just beyond 1 on the right-hand side of the graph. The next thing we want to do is find the y-intercept. So we'll write y equals, if we plug in 0 for x, anybody know automatically what's going to happen? It's just going to equal 0. 3 times 0 to the fourth would just be 0. 4 times 0 cubed is also 0. So the y-intercept is 0. And if you look at the graph, if we were to draw that in, we already have a point at 0, 0. That's when x and y equal 0 at the same time. That's all we're supposed to get, and we're supposed to sketch a graph of this function, you guys. I know, how crazy is that? All right, so we know our left and right behavior. It's supposed to rise on both sides. So that means we should have arrows up at the top on the left side and right side of our graph. That multiplicity of 3 for that first function, or that first output of 0. The multiplicity of 3, what that means is it's not going to go straight through that 0. It's going to kind of angle through the 0. So it'll kind of turn its way through the 0, not just go straight through. I know that sounds really strange. Angle through the 0. So it's going to come down from the top. Since it's supposed to be on the left side, it's supposed to be up high. It's going to come down through the top and then kind of angle its way through 0. And then it's going to go below the x-axis. At some point, it has to turn pretty quickly and come back up at that 1 1/3 over on the right. So this is kind of supposed to look like a W shape because it's an even function, but it's going to be pretty abstract looking. So let me show you what it looks like, and we'll see if you can draw it in as well. All right, what do you think? Can you see on that left-hand side as I try to draw it by, or going through that 0 with that multiplicity of 3? Notice it doesn't just go straight through, it kind of angles its way through, adds 0, turns down below, not really worried about where that turning point is right here. We're just kind of giving a rough sketch to our graph, and then comes up and goes straight through that 1 1/3 over on the right. So there's the sketch of that really bizarre looking quartic function. All right, I'm going to let you guys try this one. Sketch the graph of f of x equals -2x to the third plus 12x squared minus 18x. I'd like you to try steps 1 and 2 on your own. Well, and 3. You can get the y-intercept too. This one's pretty easy like before. See if you can determine end behavior, zeros, and the y-intercept. And then we'll talk about sketching the graph together. All right, let's see how you did. For my end behavior, I notice we have an odd polynomial function because the degree is 3. The number in front is -2, and that's less than 0. What that tells us on our graph is that on the left-hand side, the graph will rise, so the arrow should be pointing up. But on the right-hand side, the graph falls. So somewhere over here on the right, the arrow will go towards -infinity. For my zeros, when I set the equation equal to 0, I factored out the negative right away, and I also factored out a 2 and an x as my common factor. I got x squared minus 6x plus 9 left over. I noticed when I factored x squared minus 6x plus 9 that I got x minus 3 and x minus 3. It's the same parenthesis. Once I applied the zero product property, I got -2x is equal to 0, so x equals 0. And then for x minus 3, there's only one answer. It's +3. But because it represented 2 parentheses, it has a multiplicity of 2. For my y-intercept, again, when I plugged in 0, I got 0 as my output. So if I plug in my zeros at x equals 0 and x equals +3, my y-intercept is 0 as well. Notice I have a multiplicity of 2 at x equals 3. What this means right here is that's called a turning point. Whenever you have a squared function or a squared value, it's going to connect to that point and then go back in the opposite direction. So we only have 2 coordinates again, and we're supposed to sketch the shape of this cubic function. How crazy is that? On the left-hand side, my arrow needs to be up towards +infinity, and it's going to be pretty close to the y-axis because it has to go through at 0. It crosses straight through at 0, and then it's going to turn at some point and come up to touch that x equals 3 value. But then it's going to go right back down towards -infinity because the arrow has to end down here on that right-hand side. So once again, see what I draw for my graph, and then I'll have you do the same thing. When you're finished, the sketch of your graph should look something like this. My arrow on the left-hand side is toward the top, on the right-hand side is toward the bottom. It goes right through 0, 0, but then as it turns and makes its way to +3 on the right, it touches that point and then goes back to the opposite direction towards -infinity. And this is sketching the graph of higher ordered polynomial functions.